In this lesson, we'll be learning all about the second derivative test. So in a previous video, we've talked about the first derivative test. That can help us find intervals for which a function is increasing or decreasing. The second derivative test, however, can help us find intervals for which a function is concave up or concave down. So a graph that is concave up looks like an upward facing U. Concave down would be a downward facing U. Or it could look like any component of that. It could just look like the left-hand side, for instance. The point where a concavity of a curve changes is called a point of inflection. So if we take a look at this picture here, you can see that in the middle we have a point of inflection because it changes from concave up to concave down. If the second derivative is positive, right, greater than 0, positive, then the graph of f is concave up. If the second derivative is negative or less than 0, then the graph of f is concave down. Let's talk about some quick examples where we can make sense of that. So if we think about the graph of f of x equals x squared, we should know that this is an upward facing parabola and therefore it is always concave up. If I find the second derivative, so there's our first derivative, here's our second, we get 2. Since it's positive, and there's not even a variable there, so it cannot change, it's always positive, then we know it's concave up. If I change the original function to negative x squared, something we know already that is concave down because it's a parabola that opens downward, and we do the same process. We take the first derivative, then the second. You'll see that we get something that is always negative, and that's why we get concave down for the concavity of f of x equals negative x squared. So we're going to be looking at some functions that are a little bit more involved than a parabola. So for instance, number 1 is a cubic function. We have x cubed minus 6x squared plus 9x plus 2. We're going to determine the open interval, so parentheses, on which the function is concave up or concave down, and we're going to state the point of inflection. Okay, so if we take a look at our function, we start by taking our first derivative, right? In order to get to the second derivative, we have to take the first one, and immediately take the second derivative after that. So what we're going to do, it's a similar process to when we did the first derivative test. We're going to set that derivative equal to 0. And we're going to get x equals 2 as our possible x value. I'll put a note here. This is the possible x value of a point of inflection. So what we're going to do is now we're going to do the second derivative test. The work is going to look, if it doesn't already, very similar to when we did the first derivative test. So we have to just be mindful of, okay, what are we doing here? What are we looking for? In this case, we're looking for concavity. So we have to do everything with the second derivative. So we really want to think about what the question is asking and make sure we do the correct derivative test now that we've learned both. So we're going to create a number line. We're going to use our possible point of inflection value as a breaker on that number line, and we're going to pick test values. So we're going to pick something from negative infinity to 2 and from 2 to infinity. So let's say I pick 0. 0 is a nice, easy number to pick. So if I pick 0, I'm going to plug that into the second derivative. When I do that, I'm going to get a negative value, and I put a negative above the number line to indicate that. Let's say I pick 3 as my test value over here. When I plug it into the second derivative, I get a positive. So this tells me that the graph of f of x is concave down over negative infinity to 2, and it's concave up over 2 to infinity. Since there was a change of concavity, 2 is in fact the x-coordinate of a point of inflection. To get the y-coordinate, we are going to plug this into the original function. So remember, we're talking about the point of inflection of f of x. So even though when we do the number line, we're using the second derivative, here we are using the original function, in order to evaluate. So if I simplify this, I would get 2, 4 as a point of inflection. All right, let's take a look at number 2. Now we're going to look at a different polynomial one, this time with x to the 4th. So I'm going to start by taking my two derivatives. And I got my second derivative to be 12x squared minus 12x. Let's set this equal to 0. And simultaneously, I'm also going to factor out the GCF of 12x here. So my possible points of inflection are going to occur at x equals 0 and x equals 1. We're going to make our number line, use 0 and 1 as breakers, and we are going to now plug test values into the second derivative. So you're plugging into one of these two options here. Okay. Sometimes it is easier to plug into the factored version, especially if you're working without a calculator, but either of them will do the trick. All right, when I plug in a test value from negative infinity to 0, let's say I plug in negative 1, I get a positive. If you need more time to complete each test for any of these questions, you can always pause the video and then resume when you're ready to check your work. From 0 to 1, let's say I pick a half as a test value. When I do, I get a negative. And let's say I pick 2 as my final test value. I have a positive over here. So we can say that the graph is concave down from 0 to 1, concave up from negative infinity to 0, and 1 to infinity. Our points of inflection, I'm abbreviating POI there, occur at 0 something and 1 something. So what I'm going to do is I'm going to plug 0 and 1 into the original function, and each of those come out to be negative 1. All right, number 3, given h of x equals x over x plus 2, we're going to talk about the concavity and points of inflection again. Let's start by taking the derivative using the quotient rule. So 1 times x plus 2 minus x times 1 all over x plus 2 squared. I'm going to simplify that a bit. So in that numerator, I'm really going to have that 1 times x plus 2 is, of course, x plus 2 minus x. So 2 over x plus 2 squared. Now we're going to take the second derivative, once again, using quotient rule. Okay, you could rewrite it as x plus 2 to the negative 2 power as well. That would also work. So if I use quotient rule, I'm going to get 0 times x plus 2 squared minus 2 parentheses x plus 2, and then it would be times 1 in here if I was utilizing the chain rule appropriately, over x plus 2 to the 4th. It was originally to the square, to the second power, so now we're going to put it to the 4th. We can clean this up a lot. Everything over here is going to go away. And I can distribute a couple times here. So this would give me 2x plus 4. And then I'm going to multiply the negative 2 across it. So my second derivative comes out to be negative 4x minus 8 over x plus 2 to the 4th. We're going to determine now where the derivative, the second derivative, is equal to 0 or undefined. So for equal to 0, we're going to set the numerator equal to 0, and that will give us x equals negative 2. For where is it undefined, we're going to set the denominator equal to 0. That will also give us negative 2. So we really only have one possible point of inflection in this problem, which is negative 2. All right, so we are going to pick our test values, and we are going to plug into our second derivative. So like, let's say we pick negative 3 and we pick 0. Remember, they are getting plugged into our second derivative here to determine their sign. So when I plug in -3, I get a positive. When I plug in 0, I get a negative. And now we can determine our intervals of concavity. So concave down from -2 to infinity. Concave up from -infinity to -2. And our point of inflection occurs at -2. Well, we had a little bit of a problem when we plug that into the original function. So if I plug that into the original function, which is how we would normally find the y-coordinate of the point of inflection, I really get -2 over, -2 comma -2 over 0. And that cannot happen. So there is no actual point of inflection here. So even though there is a change of concavity, that point does not exist in the original function. All right, number 4, h of x equals sine x over 0 to 2 pi. And we're going to find the intervals of concavity here. So when we take our first derivative, we get cosine x. Second derivative becomes negative sine x. And we're going to set that equal to 0. We could divide out that negative, and we're really looking at the end of the day here for when does sine equal to 0. I like to use my unit circle to help me with that. So remember, if I have a unit circle, sine is the y value. So I can see over here and here that the y value is 0. So this is at 0 as well as 2 pi, and this is pi. So that makes my possible points 0, pi, 2 pi. Since we have a closed interval on this one, when I go and make my number line, I'm going to put 0 and 2 pi at the end, and then I'm going to put pi here. All right, so let's pick some test values. So let's say I pick pi over 2 and 3 pi over 2. So remember that we are plugging them into the second derivative, which was negative sine x. So I'm going to get a negative, and then I'm going to get a positive. That tells me that I am going to have a graph that is concave down from 0 to pi, concave up from pi to 2 pi, and our point of inflection where it changes would be pi, and then I'm going to plug pi into the original function, which gives me 0.